Now let us see the multiply pattern. And this pattern is exclusive for power functions. Okay, we are given a table to our right. You can see the table here. It's on this. And we have the graph on the left. And our function is actually h of x is equal to 5x cubed. So this is our function. Okay. Now let us investigate the given table for the function h of x is equal to 5x. If our x is equal to 135, if our x is equal to 3, then our f of x is equal to 135. If our x is equal to 6, then our f of x is 1080. If our x is 9, then our f of x is 3645. And if our x is equal to 12, then our f of x is 8640. Now this is the multiply pattern of power functions. So let us investigate first what's happening to the values of x. So from 3, it jumped to 6. And from 6, it jumped to 12. Okay. And that's absolutely a multiplication factor of 2. Right? So when we multiplied 3 by 2, so it became 6. And we multiply 6 by 2, so it became 12. On the other side, we have 135 becoming 180. And 1000, or rather 1080. And 1080 jumping to 8640. You can notice that this is actually multiplied by a factor of 8. So it's multiplied 8 times. So times 8, this is times 8. Now you notice that the third point, the third pair is not taken into consideration because there are instances wherein those points belong to the equation or to the function itself, but are not entirely relevant in the formation of the function. So we have 9 and 3645 here. So I am talking about this point. We are going to exclude those points because although they belong to the function h of x is equal to 5x cubed, they actually do a little, they are not relevant to the formation of the function h of x is equal to 5x cubed in terms of the pattern itself. So I'm not talking about the inclusion of 9, 3, 6, 4, 5 into the function, because definitely 9, 3, 6, 4, 5 is a part of the function h of x is equal to 5x cubed. But in terms of the pattern of power functions, there are points wherein they are not very relevant in the formation of the pattern. So from 3 I jump to 6, and from 6 I jump to 12. So let us take the case of h of 3. So our h of 3 is equal to, what is our h of 3? We have 135. And this 135 in terms of our function is just equal to 5 times 3 raised to 3, because we have a power function. So this is 135. Okay, how about our h of 6? You could see that our h of 6 is actually h of 3 times 2. Now you can see the pattern, right? And h of 2, or h of 3 times 2, is of course 5 times 3 times 2 cubed. And this is equal to, what is this equal to? 1080. And this is equal to 5 times 6 cubed, which is equal to 1080. Am I correct? Okay, now let's take a look at the last function, h of 12. Our h of 12 is just h of 6 times 2. Am I correct? Because we are multiplying each x value by a factor of 2. So we will have 5 times 6 times 2 cubed. And this will give us 5 times 12 raised to 3, which is actually equal to 8,640. So do you notice any pattern here? Like each of the x is multiplied by 2, and this gives the relevant answers for each of the f of x values. So we have 135, 1080, and 8640. Let's take a note that for here we have 8640 is just equal to 8 times 1080. So you could see that the y values are actually multiplied by 8. 135 times 8 is equal to 1080, and 1080 times 8 is 8640. So this is 8640. Okay, and 1080 is 135 times 8. And 12 is also, this is a noticeable fact. This is 2 times 6. And 6, which is not given, is actually 3 times, which is actually not seen here. It's 3 times 2. Therefore, we generalize that when you see a pattern which is multiply, multiply, so if you see a multiply, multiply pattern, this belongs exclusively to the power functions. So multiply, multiply, this belongs to power functions. Okay, so I hope that is clear enough. Now let's go to another function. And this time we have the constant second differences pattern for quadratic functions. Now you can see a given graph for a quadratic equation. Q of x, our quadratic function is q of x, is equal to 3x squared minus 17x plus 29, formed from this table of x and f of x values. For x is equal to 1, our f of x is equal to 15. If our x is equal to 3, our f of x is equal to 5. If our x is equal to 5, our f of x is equal to 19 or 19. If our x is equal to 7, our f of x is equal to 57. And lastly, if our x is equal to 9, then our f of x is equal to 119, as represented by the points on the locus of this parabolic curve, on the locus of this quadratic graph. So A represents 115, B 35, C 519, 757 for D, and E 119. Now we are about to get the second difference pattern for quadratic functions. So let us first start with the x values. Our x values gives that for every given x value here, from the previous to the succeeding, we actually get a jump of 2 units. So these are plus 2 respectively. And to our right, we have the values for f of x. And we notice that these are kind of random. Okay, these are randomly organized values for f of x. So let us see then what pattern it gives. So we have the first one, second, third, and fourth. Now the first pattern gives us a jump or an addition it's an addition of, the first one is negative 10 actually. So this is negative 10, and the other one just jump to positive 14. And then the next one gives 38, so plus 38. And the next one gives us 57, 119, so that's like 62, right? So plus 62. Okay, we couldn't see any pattern in here. We have negative 10, positive 14, 38, 62. There is no, it doesn't show any pattern yet. But looking at the second difference, so let's go to the second difference, which means we are going to subtract the given subtraction or the given units from getting the difference from the previous to the succeeding x value for the first difference. So now we get the second difference, and you could see that this pattern gives us plus 24 here, and this is also plus 24, and the third one also gives us plus 24. Now we have a pattern. We saw that for every shift in the first difference from negative 10 to 14 to 38 to 62, now we could see a clear pattern for the second difference, which is an addition of 24 units for every succeeding value for f of x. So therefore, the differences between the corresponding y values are now equally spaced. So the differences between these differences, the second differences, are constant, and this constant is equal to 280 square. So this second difference is actually equal to 280 square, which gives us our value for the quadratic function, giving us the square unit, which is twice the coefficient of the quadratic terms times the square of the difference between the x values. So what does that mean? We have twice the difference, twice the coefficient of the quadratic function. Our quadratic term there is 3x squared. So the coefficient of our quadratic is actually, what is our coefficient here? Our coefficient for the quadratic term is 3. So that gives us 2 times 3, which is equal to 6. And the square of our common difference, so the difference between the x values, for example, 3 minus 1. We get the first x value and the second x value. So 3 minus 1 is equal to 2. And it says that we have to square it. So that's equal to 4. Therefore, we will have, 6 times 4. And that gives us the second difference. Okay, this is our second difference, which is 24. And relatively, it gives us a confirmation of the second differences based on the table. So therefore, if we see a pattern of second difference, then this is actually exclusive for quadratic functions. So for a constant second differences pattern, constant second differences, This is exclusive, of course, for quadratic functions. Okay, so I hope this gives you a clearer view of the patterns. We have the first pattern. We have the add pattern, and that's exclusive for linear functions. The add multiply pattern, which is exclusive for exponential functions. The multiply patterns, which is exclusive for power functions. And finally, the constant second differences pattern, which is exclusive for quadratic functions.